All right, let's start. Welcome everyone. My name is Eli. I'll be your host. So a little bit of introduction about myself. I'm a data scientist, also software engineer and platform engineer. And I've been working into the AI field since 2014. And also academically, I'm graduated from Columbia University in the Department of Engineering, and I have a postgraduate in artificial intelligence and machine learning. So today I'll be presenting on behalf of Facile AI. So Facile AI is a little bit about Facile AI. Facile AI is a company that started as just a gathering of hobbyists in Sydney, Australia. And it started with the name of Fall for Data. But then as more people were joining and discussing and sharing knowledge, this evolved to something that could be useful to everyone. So Facile AI currently is still based in Sydney. It hasn't an outreach outside. But the main mission of Facile AI is, so before I talk about the mission, first I'm going to do a disclaimer. This webinar will be recorded, which would mean the videos that I'm recording now could be used by Facile AI for other purpose regarding Facile AI mission, which is mostly teaching. All right, so let's go on and talk about what Facile AI does before we can then start the webinar of today. So Facile AI is an organization that was established with the aim of helping many other, especially mid-sized organizations, to become data-driven. So we do that by helping companies to develop effective data strategies and to build strong data sciences teams. So that means we also help organizations with how to structure a data science team and what kind of skills to look for when hiring a data scientist or a machine learning engineer. We also help with providing practical ML trainings. So that's basically about Facile AI. So now let's start for the aim of today. This today is not about Facile AI, but it's about MLops. So the topic of today, the MLops topic, it's a topic that normally when we do this, we provide this as a training for the entire day. So I will try to compile this content within 1 hour, if I can. And to do that, I will try to avoid anything that requires me to run. Then I will try to avoid it so that we can move faster. But I'll make sure that the code and the other materials that I share will be visible and well explained. And also at the end of this webinar, I will email you the link to the GitHub repositories where the code is hosted. So during the presentation, if you have any question, you can type in, and then I will be able to take a pause after half an hour, and then I will respond whatever questions will have come through. All right, so before we talk about MLOps, let's think, why do we need MLOps? So to do that, we need to take an analogy between MLOps and the classic DevOps. So with DevOps is this process of being able to develop your code locally or on another environment to use for development, and then being able to ship that code to a production environment smoothly and being able to trace errors during the process. That's CICD. So that involves two concepts, as we can see here. On the left, the CI concept, the CI process is where you build all the artifacts that you need within your code. So that includes running the testing, building Docker images, and anything happen within that step of CI. And then you have the continuous deployment, the CD, where you actually release and deploy the code to a server, and then you monitor the code. So that's for the normal programming. But when it comes to machine learning, it becomes a bit trickier, because machine learning, it's not only you will be dealing with the actual code, you're also dealing with data, but you also need to know, after you deploy this data, how much the change in the data that's coming to production affect your model that you deployed. So in other words, I would say with machine learning, the MLOps will have mainly three major parts. The first part is called the ML part, where you build the model and gather the data, train the model, and then there is this next step, which is making that model ready to be shipped. So in that stage, that's where you create the code for inferences, and then you package them into a Docker, and you do some sort of verification, and then you release for production. And then from there, you have to run some sort of monitoring. With the classic coding, by classic, I mean with the coding that's not artificial intelligence, the monitoring will be the performance of the server. The monitoring could also be something like how many, what the frequency am I getting? Am I getting error, 200, 500 errors, and so on? You know, those things that you get when monitoring a server. But with machine learning, on top of that, you also need to monitor the performance of your model. Is the model decaying? Is the model still performing as you expected? Or is anything happening in your data that could make your model to no longer perform as it should be? So that's what we are going to look at today. We are going to focus on that part following this graph. So this is the graph that shows how the MLOps workflow works. So in a typical machine learning project, you will have a process where you have to prepare for data ingestion. So that's the data ingestion will be the process where you get data from different sources and you want to get them in one place where you'll be able to access them and then therefore be able to do some sort of machine learning processing that you want to do. And then after that step, you move to the next step, which is data preparation. In the data preparation, that's the steps where you do things like normalization, especially when you have data like numerical continuous data, and then you want to put them in within the same range, then you do normalization. There is categorify, which is mostly for categorical data, and then you also do things like feature engineering. Then once you pass that step, you want to get to data versioning. So because with the data that you have, it will also impact your model. So you need to be able to reproduce the experience by versioning your data. So if you trained with a particular data, you need to be able to come back to that data and rerun the training if needed, or being able to look at data. So this stage of data versioning is a stage very important. And then after that, after you've versioned your model, your data, you need now to run the training. So in that way, you build something, you build some code for running a model, you do hyper tuning, and then you do the model selection. And once you're happy with what you've done, you run your model, you build it. Once the model is run, you have to register also the model. So registering a model is similar as what you do with data versioning. This is also a way of giving you a way of being able to go back to the same model and use the same artifact that was packed within that model. And then after that, you pull the model from the registry and then you deploy for inference so that people can use it. And from there, there is a long process which is of monitoring what the model is doing. So the whole process is covered under what we call continuous training. So for today, especially we are going to focus on the model training. So we're not going to focus on data ingestion, data preparation, data versioning. I have already prepared some data that's kept somewhere, which I'll show. And then we'll focus on building the model and then registering the model, deploying the model, and also the monitoring part. All right, so let's move to the big picture. So this part, model training, model registration, model deployment, model monitoring, can be expanded into something that looks like this one. So what you see in this picture is exactly the code that we are going after a few slides, the code that we are going to explore. So basically, the picture shows two repositories. It shows two repositories. The upper part is the part of the training of the model or the continuous training, and then the lower part, which is highlighted in red arrows, is the inference part. So you basically need to think the model as your MLOps operations as made of two separate processes. The first process is the continuous training. This is the process that starts from when you train the model to when you actually build it and register the model. And then the second part of the inference starts from pulling that registered model and run it and expose to an API so that people will be able to run that model. So that could be online inference. There could also be offline inference. Regardless, it's still an inference stage. So what we suggest into our MLOps workflow, we suggest a separation of those two. In the first stage, you build the continuous training, and then you have a separate repository for that, all right? And this repository has two branches, the dev branch and the main branch. And then you have also the same thing for the inference. You have a GitHub repository for the inference, which also may have different branches. And then for any commit that is made to the branch will get orchestrated by Azure DevOps. So the Azure DevOps will be the tool that we use for our CICD. We'll be able to connect to the registry, understand that there has been some commit either on dev branch or main, and then accordingly, it will trigger a step of build. And then after that, it will release the model to Kubernetes platform. And then the Kubernetes platform model will also start feeding data to the monitoring engine. So this part of monitoring engine, for the sake of this presentation, it's decoupled from, it's not automated, but I will show you the script and then we run a little bit of monitoring to be able to see how the model decay. Okay, so this, don't worry about this. This will become clear as we look in the code. We'll see this kind of separation. I was just showing how this will go. So now let's talk about the steps you go through. This was the big picture for the whole MLflow, entire flow. And then now this is the steps you go through. First step, when you build your model, you need to do experimentation. So the experimentation step, this is the step where you write your code, your model, write quickly something, run them, keep tracking, find out which parameters are working for you. And then once you are happy with your experimentation, the experimentation will generate some artifact. The artifact will be the features that you chose, and it will be also the best parameters for your model. And then those will be used to go to the next stage, which is CICD for the training, for the continuous training. So now you have to build the best for CICD using the artifact that was generated by the experimentation. Now, once you pass that first, because the CICD training has generated a model which got registered somewhere in a registry or a storage, then you have to build the inference, which will also get deployed to Kubernetes. After you have that inference, then you have to keep watching for the data that's coming to that Kubernetes via this last step, which is data and drift monitoring. Okay, so we're now going to look code for each this step. Starting now, we're going to start with the experimentation. We'll look at an experimentation made of xgboost, and then we'll hypertune using Optuna, and then we'll use Explainable dashboard to analyze our built model. After that, we'll also, with that, we'll also run at the same time the MLFlow to track the experimentation, and the Python will be the programming languages. For CICD, we'll see Azure DevOps. We'll use Kubeflow to create pipelines, AI platform to deploy easily Kubeflow, and then we'll have GitHub. We'll have GitHub for as a repository. All right. So for the experimentation, as I explained, this is what we are going to do. So let's open the code and go through the first stage, which is experimentation. I hope you can still hear me. Okay, so, all right, so let's go to the code. So, just a second. Yeah. So for the experimentation, I'll be writing my code inside Jupyter Notebook to make it more easier to read. So the data set that I chose to use today is a data set, obviously because I'm based in Australia. So this one will be about Australia. So this is a data set that was provided in Kaggle, and it's called Melbourne Housing Market. And the data set basically has this. So this is what the data set. Are you guys able to see the screen, or you want me to zoom in? Okay, so let me know if you can't see. Okay, so I'll make it bigger. Okay. So this is the data set. Maybe let's explore it straight from Jupyter. Yep. All right, so the data set will have suburb. So suburb is the name of the location, and then it will have also rooms for each property. It will have the type, so the type whether the house is a house or unit or semi-detached, and then we'll have the prices, and the exercise will be to build a model that can approximate the price, and this is everything that was given. So I'm not going really to focus on the model itself because the objective for today is for the MLOps. So we'll build just anything, and then we'll see how we deploy that. So this is the data set. Then here we have just some functions to export the data set, to export the data transformer. I will share this code, you can go through, but the most important thing here is we are pulling the data set, and then I defined continuous features and categorical features. So for continuous, I chose these ones, and then for categorical, I chose these ones. And then I get the data, but then when the data, so I added on in here in this function, the function will get the data path and one parameter which could be true or false. So this parameter will be used to tell this function that this is not hypertuning exercise, this is the actual training. So they're going to be a hypertuning phase and the actual training phase. With the hypertuning, there will be that phase where you just keep trying a lot of hyperparameters to see which ones will work. And then with the actual training, you will just train with whichever parameters you found. So we want to be able to say, if hyper tuning is not true, which means if we are not hyper tuning, let's save the artifacts that we use. In this case, let's save the features that we are using. At the same time, let's also save the data processor. So the data processor will be the one that has the statistical properties of the data, like the mean, standard deviation, and so on. We want to be able, when we fit the model, we want to be able to use the same feature that we used, the same statistics that we used during the training. So that's why we need to also save this as an artifact. All right, so I will let you go through this process. So now this get data will return data that has been already transformed using FastAI tabular pandas, which is a FastAI class used to transform your data. And the reason I chose this one is one of the fastest data processor that you can find out there in the market. I compared it to other variables such as scikit-learn, and I found that this one was outperforming scikit-learn in terms of data processing in a very big way. So I could, for the same data set, scikit-learn was running about 3 minutes, but with this one, it runs just a few seconds and it's done. So it's a good thing to know. And then you get, this will return the training data. And then we build also the function for training. And in this function, we want to run the MLflow. So the MLflow, this is something I didn't mention. The MLflow is this one, MLflow. For those who never heard about it, MLflow is a platform for experimenting, tracking, and deploying and registering models. It's an open source, but we'll be using this one. So basically what the MLflow tracking does, it helps you to log all the parameters of your training as you train, and then you'll be able to have a nice dashboard where you can see what's happening, and then you can compare which one's running. You can also copy the parameters that's working. So now to do that, this keeps, yeah. So to do that, you have to start a session for MLflow by doing something like this, MLflow run, and then you precise what's experiment ID you want to run. And then you do the normal model training, and in the end, make sure that you are logging the parameters inside the MLflow. So I'm not going through the details of the ML because I will share this file, and then you can go through them line by line. I don't want to deviate the focus of this subject to building model, but rather just to keep on the focus of MLOps. So I'm just showing this to show that this model is having some sort of hyper tuning happening, and we want to be able to understand once we read this file. All right, so another thing we need to do, we also need to build the objective function. So Optuna, which is the platform that I'm using for tuning, it's this one. It's a hyperparameter optimization framework for machine learning. It's a very good one. I recommend it. So the way the Optuna works, you build an objective function, and then you tell it whether you want to maximize or minimize the objective function. So in this case, we want to minimize the root mean square error. That's why we create the objective function. We return the root mean square, and then we pass this objective function to our Optuna. This Optuna, we tell it, take it's here, take the objective function, all right, and then minimize it, okay, direction, minimize it. So we need just to create a function which return the root mean square. So this will get the root mean square from the training. For each iteration, we return the root mean square. And then this will be passed to the obtuner. And the obtuner will try to figure out which parameters will minimize this objective function. All right. And then we run the experiment. All right. So in the experiment, we tell it we want to hypertune. If it's hypertuning, then we'll run via obtuner. If it's not hypertuning, then we'll copy whatever good parameters we found from obtuner and use them. Okay. So now next thing, after that, we run our function, we run our experiment by creating an instance of MLFlow, and then we also tell it that we are running a hypertuning exercise. So the experimentation we run here as we see, and then it will run an amount of trials that we tell it. So at the beginning, we tell it, let's run 30 trials, okay? So it will run 30 trials. With this trial, what I mean by trials, it's this one. As you can see in the objective function, we provided some range of parameters. I'll make it bigger. Okay, so we said for the booster, choose just GB3. So we are only providing one booster. But for things like subsample, the obtuner will try to find the best parameter between 0.6 and 0.8. For call sum3, we'll try to find between 0.4 and 0.7. And then for number of estimators, these are trees. We will try to find between 140 and 200 trees, and so on. So you give it a very long list of range where you want it to find the hyperparameters. And it will be using Bayesian optimization to find which parameters are the best. Okay, so it will run 30 trials. So for each trial, it will pick, using some statistics, it will pick which one is likely to be the good parameter by looking at this optimization objective, the minimization, this one. So now it will pick in the range, and then the next iteration, it needs to do better because it will be looking within this. You say, should I move to the left or to the right? So it keep doing better, better, better. Hopefully at the end of 30 trials, it will have found optimized hyperparameters, and then it will log that for you so that you can use them. So we run 30 trials. This will be first trial, second trial, and then we'll keep running to the end. After it finishes, it will give you a summary of what it has done. It will say, I've run number of trials equal to 30. I've run 30 trials. I found the best value. So the best root mean square I could find was this one, 279,000. And this is the optimized parameters. So now remember, in our code, we said, so you can also print this graph to see if it has been actually learning. So you can see that the trend was going down, which means this model was actually learning properly. So now remember, in our code, we mentioned that if we are hypertuning, if we are not hypertuning, then save the best save the model. That's one. Okay. Now we need to go back and make sure that we do hyperparameter set to false so that we can save this model in the artifact, which will be deployed with this model. So to do that, we just have to run again the model and make sure we set the hyperparameter to false. All right, so we run the model, but this time the hyperparameter is false. So what the model will do will say, okay, this time I will have to use the existing parameter that was saved as part of the hyper tuning. So the model will start training, but instead of instead of just working as before by trying to run through different parameters, this time it will just run by these parameters that we pass it. Okay, so we'll load this parameter, we pass to the model, and then we run, and then that will create the artifact. And that will be the end of the first experimentation. Now, I talked about MLFlow. So as you were running these hyperparameters, the MLFlow was running. So remember here, we created an instance of MLFlow. Here, we created this instance of MLFlow. This instance, every time for these 30 trials, it kept logging every parameter that we received here. Okay, so for every trial, it created these parameters. Okay, and then in the end, it saved them during the training here. Okay, it also saved here. All right, so we now want to open the MLFlow and see this parameter and see which one actually worked best so that we can be sure that it's working. So to do that, we'll go to the base. I'll make this big because I know you may not be able to see. So this will be, I created a folder called local. That's where my code is running. So in the local, I will see that the local so the local, this file local, you see that it created a folder called ML runs. This is where your MLFlow will be logging your experimentation. So it turns out that during the experimentation, we're using experimentation number 2. So it created all this experiment into folder number 2. So we need to load this by doing, I need to activate first my environment, and then I need to do MLFlow. So you type MLFlow UI, and that's it. This will run a server. It will tell you which the server where it is, and then you copy, open it, and run. Okay, so now the experiment is number 2, which is this one, experiment number 2. And as you can see, it has logged for every iteration all the parameters. See, all the parameters and the metrics. Okay, so now we want to see which one has won. We can do something like metrics dot RMC, because I'm interested in the root mean square. So I can just do look for whatever is the best here. So I can say, find me the RMC that's, let's say, less than 80,000, 280,000. So this will run through the whole experimentation. It found all these are actually less than. So we can even look for less than. We can say, what about 75? So there is nothing. What about 75, 500? 75, 300. Okay, so you minimize. For now, you see we have a shortened list. I can even go and see that there is 11. So I can do something like 75, 12 instead. And I get less. So now looking at this list, I can tell that this and these ones are winning. So I can go into one of them, have a look. I can see that it's actually these parameters that were good. I can look at this. I can also go back I can also go back and choose, let's say, 1, 2, 3 of them, and then compare. So this will give me a nice view where I can compare different runs. I can also see how different they are in terms of root mean square. I can see that this run is the best, okay? And yeah, so there are a lot of things you can do. You can look at this graph, see which one is the best. You may see it's this brew, and then you can go into the individual one and so on and get all the variables. So this is just to show you how when developing locally, the things that you need to do before you can ship your model to a CICD. And after that, you also need to be able to look at your model that you just trained. How did it do? Did it do well? Okay, so to do that, I have this thing called explainer. So what the explainer does, the explainer will take your data, do some sampling, and then start an instance of explainable dashboard here. Okay, so I've already started. So the way you start the dashboard, it's quite easy. You'll just type in, hang on. So you type something like, oh, all right. So you just run this file, python.explainer, and then it will open an instance. So I've already have them open because the explainer take time to load. So I already loaded one. So this is an example of the explainer that I just trained. So in the explainer, you will have these 6 tabs: the feature importance, regression start, individual prediction, what if, feature dependence, decision trees. So in the feature importance, you get a listing of the feature and which one are the most important. All right. So by looking at this feature, you can see that up to this feature number 12, the rest of the features were almost useless. Okay. So this tells me I can go back to the model, remove this, and retrain the model, and my performance will almost be similar. So the performance of this model, as we can see, the root square mean is this one, root mean square. We can see it shows other things like predicted versus the actual. So this is, as you can see, this model isn't really fitting properly. It was trained on small trees. It just going far from the predicted. And I can see things like the residual analysis. You can do things like prot versus feature, where you choose a feature and see how the residuals will change depending on that feature. You can also have things like individual predictions, where you look at for each feature, how much did it contribute to the prediction. All right, so this, I will leave this to you so that you can go through. This is a very nice tool. It's a very handy tool for analysis of your model. It also gives you partial dependency plot. For instance, here you see you have distance, and then it will tell you as the distance increases, the prices has reduced. Okay, so the predicted prices was decreasing by the distance. And this makes sense. The more, so this distance was the distance from the central. So the more you go far from the central of a city, the houses will become less expensive. And this is what the model is telling you. It's telling you as you increase the distance, the prices has decreased. And you can try that for other things. For rooms, for instance, it's saying as you increase the number of the rooms, the prices increased as well. So this is a nice way of analyzing your model before you can decide to put it on production. This thing called what if is where you can make your own customization. You may say something, what if rooms, everything stayed the same, but rooms increased by 1? What would have been the impact? and then it will show you the impact happening. So you just try to balance, and this gives you more understanding of why the model did what it does. All right. So this was one explainable dashboard. Then I created another one after removing the unnecessary feature. And then I trained, and I got the same, I got the same performance. All right. So now we've got the model that we've trained. So now the next step is, let's take this model and do the actual CICD to push this model for the continuous training. That's what comes. So we had just finished the first phase, which was, so we had just finished the experimentation. We've seen the xgboost. We've looked that we used Optuna for hyperparameter. We used MLFlow to track different runs, the parameters that they generated. And then we just seen also the explainable dashboard, how it tells you what features are important and how did they help. So now we are going to look at this CICD first, but as I promised, let's take a 2 minutes of break, and then I'll look if there is any question that I can answer, and then we'll continue to the next phase. Okay, so yeah, so someone just asked, what is the explainer dashboard? So the explainer dashboard is a framework. It's an open source. I'll show you the website to make sure. So the website is Explainable dashboard. So this framework, what it does, it helps you to, it's not like Tableau. Tableau will, so you're asking, is it like Tableau? No. So Tableau is for business intelligence. You get some data and you do analysis on the data. But the Explainable dashboard, what it does, it takes the model that you build and run against data that you provide. And then it will see what thing, well, the most important for this model to make the prediction. So it gives you information, clear information about why the model is doing what it does. Explainable dashboard come part of what is called Explainable AI. As part of regulatories, many countries are asking MR engineers to be able to explain both to the organization and to the consumer what the model used to make decisions that it has made. So the Explainable dashboard is this framework which will do that for you. So basically, if I go back quickly to one of the dashboard that we were looking at, this dashboard, yeah. So for example, we were looking at this example where the Explainable dashboard looked at the model, and then it found that the model, during the training, it found that the distance was the most important feature. So it found that, oh, the more you go far from the central, the prices will reduce. The more you get closer to the central, the price of the house will increase, okay? It also found that the rooms were also another important feature. It found that the postcode, definitely the postcode is the location. So we know that the location will also count. It found the type of the house, whether it's, so all these things are the things that the model ranked as the most important thing, okay? At the same time, it gives you also other statistics that you want to know, like what are, well, the root mean square, that like this root mean square error, how big was it? It also gives you other interactive way of analyzing your model, for instance, by looking how each feature of the model contributed to the prediction, what the impact. It also shows you how this, the predicted prices changed depending on a feature. And there are also many other things. So I can't go through all of them. There are many. If you go into this Explainable dashboard, you will really find it very useful, and then you can play with it. I hope I was able to answer the question. Yeah, no more questions. So let's go to the next phase. So this one, the next phase is kind of, I don't know how to say, it's kind of trickier or maybe confusing given that we are using Kubeflow. And for those who played with Kubeflow, you will find that Kubeflow isn't an easy thing to learn. It has a lot of confusion when you start using it. Either way, I will take you through so that it become easier for you to understand. So I'll try my best. So let's go through the Kubeflow first. I'm going to show you what is Kubeflow for those who don't know it, and then we can look how to deploy such a pipeline. So Kubeflow is an open source framework for generating machine learning pipelines. So by pipelines, it means for all those steps that we saw in the machine learning pipeline. So if you remember, we saw the steps of getting the data, transforming the data, building the model, register the model, deploy, create the inference, do the whatever, the audit and so on. So that's a pipeline. So the steps goes from 1, 2, 3 to the last. So that's a pipeline. Kubeflow allows you to create graphs where each graph will be connected, will have nodes connected to each other, and that will be a pipeline. So here, for instance, I have a pipeline that I created, okay? So this pipeline is called Melbourne House Pricing Pipeline. And what you'll see, the pipeline starts with submitting a crowd training. So as I said, I skip the phase of data. I'm getting the data straight from somewhere in a storage. That's why there is no graph for data. So it will start by training. After you trained your model, you do the evaluation. After you made the evaluation, you need to add a condition. You need to have some sort of metrics. Let's say you may say something like, if the root mean square error is less than this value, then deploy it. Otherwise, don't do it because it's worse. So you basically want this pipeline to deploy only when it shows promising values. So this is what condition mean. You're adding this condition to validate between the value you got from the evaluation, whether you should trust it and deploy it for inference or whether you should just throw it away. So this is the pipeline, the graph, and then it has a YAML file, which is basically the definition file. This is the manifest that creates this graph. Now, as you can see, this manifest is really too big, okay? You can't create it by typing each line by line. It becomes very hard. So Kubeflow provides a way of making this YAML file by generating them. So you just write your code in Python, and then they get transformed into this YAML file, which get deployed. So I will show you how to make that Python code which generate the YAML, which get deployed to create a pipeline, okay? So now once you have this pipeline, you can run experiment on the pipeline. You can do the runs, okay? So to create a run, you just click here, you choose the pipeline. So don't worry, I'll show you how to create a pipeline, but as of now, I just want you to be familiar with the tool. So you choose the pipeline, you give it a name, some name. So the name could be something like the name of the pipeline, like this, and then you add something like run number 1, okay? And then you basically choose the experiment if you created one. So in this case, I have one experiment. So the experiment will help you to group different runs into an experimentation so that you can find them easily. And then you choose whether you want to schedule this to run recurringly, either periodically or cron job and so on, or whether you want to run it one-off. And you specify, so this is because we are running this on Google. Google requires that you specify which project where you want to run. So the Google project in this case is the Facile AI Dev. So I need to specify that so that Google knows deploy this, run this deploy the containers for this run within this project, okay? You also tell the region for where you want to deploy the experimentation. And then this GSS route is basically the path where you want to save the artifact that will be generated. So this most of the time it needs to be your storage. It could be on Amazon, could be anywhere. So for me, I usually use the cloud storage. So you just specify which path. So let me open mine to show you the example. So this is my cloud storage. The artifacts, sorry, so I will give it something like this one, okay? Deploy whatever you create inside Facile AI Kubeflow default staging, okay? So I have it open somewhere, I can copy. Yeah, so this is the path. All right, so I can go back here, put the path, and as we saw, I'm calling it staging. So basically, I'm telling the run, whatever I generate, place them in the root folder called staging. And then I'll also precise what type of metrics I'm interested in. I'm interested in root mean square error and the threshold. So that you remember that condition, it's looking at the threshold. So I can say something like, if less than 400,000, then deploy it, okay? So after that, you just run, and then that will create a run, and that run will just create something similar to this. For this, it will start by here, creating a Docker file. This Docker will run. Once it finishes, passes the value to this one, to the end, and that's how your pipeline will be working. So this is the pipeline that we are going to build. So let's go to the code and build the pipeline. So I'll cross this to not distract you. The pipeline is, sorry guys, the pipeline, I have it in the folder called Melbourne House Prices AI Platform CICD, okay? All right. So this is the folder. Now, to create a pipeline, there are some, I would call them rules that you have to respect, or the things that you need to follow. The first thing you need to do is this pipeline, all right? So that's why I'm saying it's kind of a tricky one. So every step that you see here, each box that you see except the condition, so everything except the condition is a Docker file. It's a Docker container running. So Kubeflow allows you to run every single component as a container that get deployed to Kubernetes, right? So now we need, when we create our pipeline, the very first thing we need to do is creating those Docker files, okay? So the easy way to organize them is you will have a folder called the trainer image. So this is where you put your training Docker, okay? And then you also need, because the Docker will be deploying this trend.py, you also need to have the trend.py. So this trend.py, it's the same trend.py we had here, except that I just changed it to remove it from Python, from the notebooks to just a normal Python. Okay, it's a normal Python file, but everything else will be mostly same. So this will be the same function. Okay, this will be the same road artifact. Everything will be the same. You will just removing things that are related to notebook. Another thing I removed, this is me. This is something you can keep or let. Another thing that I removed Optuna because I don't want to hypertune from that pipeline. I hypertuned during the training with MLFlow, the one that I was showing you in the first part, and that I already saved the hyperparameters into the artifact called parameters.txt. So I just need to keep using that for the actual training. So I removed the hyper tuning, and that's it. And also there is also this thing called fire so this is fire package. It's just a package that allows Google to be, when the Docker file is loaded, so when this trend run inside the Docker, when this fire run, it will be expecting to receive parameters of whichever function you provide. So you see here, this function has 1, 2, 3 parameters. So the dataset path, the training dataset, the validation dataset, the artifact path. Remember, the artifact means the path where you have stored your features, and the file that contains your features, and the file that contains your parameters. And then this job directory is basically another path where Kubernetes will just keep saving the job. So this is automatically generated by Kubeflow. You just add it, but you don't provide it manually. So what we'll do, this file will get these variables from when you run your container. Kubeflow will run a command prompt, the terminal code to pass these parameters to this function, and the training will kick off. So it's not hard. I'll leave this to you, but basically, I wanted you to make sure to know that the trend.py that we have under trainer image is the same trend that we used during the phase of experimentation. And then you just add this Docker. One thing you have to remember, because you're running this on Google platform, then always import this base CPU image, which will have everything that Google need to use to be able to run your project. But then you also need to specify other specific packages that you want to run, okay? For example, Panda, FastAI, xgboost. So these are specific to the trend.py. And then the entry point will be python.trend. So the Python trend will run this Docker, and that's it. So notice that it will just run on whichever port that this one will decide. So I didn't have to do anything like expose port. This orchestration will be taken care by Kubeflow. So no need to provide the port. All right, so after that, I showed you the first folder. You have another folder called base image. So you always need to have, this is just copy paste, okay? So the base image, what it does, the base image, it's just basically running this, whatever other packages that you need, you specify them so that they can run by the Docker. As we start looking at the code, you will see why you need the base image. So let me skip for now. And that's pretty much of it. And then you need something called the pipeline. So this pipeline folder, that's where you define the code that creates the YAML file that I show you, the manifest file. So this is the file. It's written in Python, and then I'll open another called helper. Okay, so I'll go straight to this one, and I will explain line by line. So this code it uses an API provided by Kubeflow, and this API will help you to get whatever you program here and transform them into a graph. It will transform them into that pipeline that I showed you. So there are things that you need to comply. For instance, because you will be running everything as Docker, you need every variables that you need to get from at the top level, you get them as environment variables. So this will allow external services to pass these values to the actual, to this file during the compilation. Okay, so, and then you specify the training path. So remember, I'm in the URL, when I was showing you the trend, this trend file, this one, I mentioned that the function for training is expecting training dataset path and validation dataset path, okay? So this one, you need to provide them via this file, okay? So that's why you need to define here the path for the training, the validation, the test, if you need them. So in this case, I'm just saying dataset training data. So this is how I organized. You can organize it whichever way you want. But then these values, because we are running in a Docker, there will be just the path after the staging. So remember, when we run the pipeline, we provided a storage URL. I keep going back to this to make it easier to remember. When we were creating a run, here we provided sorry. Oh, sorry. I'm opening a run. That's okay. So when we were creating a run, pipe run version. Okay. So, all right. So remember, when we were creating a run, we provide this GSS route. So this is the route, as I said, that goes here. Yep. So here, okay, to the staging. So basically what the pipeline code will do, it will take that route and then add this after that so that it will be able to access dataset, artifact, job deal mode, as you can see, dataset, testing, and then you have data, okay? So this is the same thing. So dataset, training, data, okay? So I hope that's clear. And then you initialize your component, you specify which component you will be using, okay? So in this case, we tell download component from this URL. So every time you'll be using this one, and I've never seen anyone using a different one. So you'll be using this component URL. I will show you the URL. It's always the same. The version change depending on a new Kubernetes, but if you're using a particular version, then this value will always be static. And then you specify your component. So component is this. When I talk about component, I'm talking about the pipeline element. Each box, each box except the condition, each box is called component, okay? So when specifying in this Python, you need to specify components. So the first component is called ML Engine Training Op, which is component for training. It turns out that Google had already provided this, okay? So there are people who develop this component. You just import it and run it. So you don't build any custom code. You just use it. So we need that one. And then there are two other components, one for evaluation, which is a custom component. So we're not going to use an existing, we are going to create our own because we want to do evaluation on our own way. That's why I provide function container op. And then we pass it a base image. So remember when I skipped the base image, I said every component need to run as a Docker. And for the training, we already built the training. So I showed how we build it. I talked about this training, but then we had this one called base image, which is kind of empty with a Docker file. And then you may be wondering, why is it there? This is why. It's because you want to use it as your base image for your custom component, okay? So you have it here. I defined two custom components, and then this component will run code that we have to define. And how you define them, you define them just here. I created two functions, okay? The first function is called evaluate model, which is basically taking the dataset path and the metric name, okay? And then output the metric name and the value of the metric, okay? So that's the definition of the function. And then in the function, you're doing basically what you have to do, which is download the model, run the data processor to get your data transformed, feed the data to your model, okay, predict from the data set that you downloaded, the test set, and then evaluate the mean square, the root mean square if you provided metrics as RMSE. So remember, when I was creating this, at some point I was specifying RMSE as my preferred metric. So this is where it gets useful, okay? So if I said MSE, it could have returned this one. But because I'm using RMSE, it will return the root mean square of the evaluation, okay? Of the predicted. So this is for the evaluation. So basically this function will create here, evaluate the model. Now I have another function that I call run Azure pipeline. So this is with this one, run Azure pipeline. So the run Azure pipeline, what it does, after the evaluation has passed and the condition have been met, the run pipeline will just trigger an API which call Azure pipeline to deploy. So we haven't talked Azure DevOps yet, but once we go to Azure DevOps, I'll come back to this component and then it will make more sense, okay? So, but at this point, just consider it as the code that make the actual deployment of the inference code, okay? So now I've showed you these two helper components. We use them here. See, I pass it the evaluate model, which is the function that we defined in the helper. I also pass the run Azure pipeline, which is also another function that I just showed you. So basically, after you've done that, then the next thing that follow is mostly about defining and then calling the actual component, passing them the parameters. So this is the component for training, the one that we defined here, this one. So this is where you pass it the actual values. And as you can see, these values is almost the same values that we had in Kubernetes, in Kubeflow. So the project ID, the region, you tell it which image, which is the trainer image that we built here. And then the argument. So these arguments are other arguments that the training will use, such as the training file path, the validation, the artifacts directory. Okay, so you also do the same for the evaluation model. You pass you tell it the dataset path, but one important thing, the evaluation model, you want to tell it where to find the model, and then because if you remember into the presentation, I mentioned something about model registry. So this is where it happened. When this ML engine train runs, so by that I mean when this thing runs, it creates a unique location into a storage that you specified, and that unique location will be a unique ID, and then it will keep the model inside there. So that's how it version your model, okay? And that you will be able to use that unique ID to identify where the model is. And that unique ID is called job deal, okay? So here we are telling the evaluator, can you download the model with this ID, okay, with this version, and use this metric name to evaluate it. And then we initiate the condition. So the condition, that's the one here. This is the condition. We initiate the condition and we run this one. So this code have created, it has created the graph for us. So it's still Python, but now we need to compile it into a graph. Now to compile it, that's where Azure DevOps comes in, okay? So for Azure DevOps, I could run this code directly on my computer, but because I want to automate things, I want to make sure that this thing will run inside Azure DevOps rather than running on my computer. So to do that, I would just create an Azure pipeline. So this is how Azure DevOps works. You create a YAML file. you tell the stages that you want to do. So let me go to Azure DevOps quickly to show you the stages that we created. So this is my Azure DevOps. I'll go in Facile AI. The Azure DevOps has also pipelines. So this is basically the CICD. If you use any other tool for CICD, you can use that. I chose Azure DevOps because I'm familiar with it and I like it, but you can use Jenkins and anything else that you like. Basically, what you have to do is just create a pipeline. So I have the pipeline already created for you. So the Azure DevOps, let's, for example, I'll go back. Let me edit the pipeline to show you. So this pipeline is just connecting to this GitHub, okay? And then it's looking for the file Azure Pipelines, which is exactly this file I have here. So this code will be pushed to GitHub, and then Azure DevOps will pick it up from there, and then it will look at this definition, okay? And part of the definition, there are going to be this one stage at which I build the base image. So the Docker image that we show for the base, I will build it at this point and send it to a repository in Google. I will build the training image, send it to a repository, and then I will compile that Python code. So this Python code, the one that creates the YAML manifest, will be compiled here with Azure DevOps at this stage. And then after that, I will run another stage for deploying this to Kubeflow, okay? So to deploy to Kubeflow, there is a code for that, which is KFP endpoint, and then you specify the endpoint of your Kubeflow. So the endpoint of your Kubeflow will be, you can find the endpoint by going to AI platform, dashboard, and pipelines. And then here in settings, the endpoint will be this one, okay? So that's the endpoint. All right, so the endpoint, you just specify the endpoint, and then this thing will be sent to Kubeflow, okay? So that's how we created a CICD pipeline that looks like this one. This CICD will basically do, it will build, and then, this is a wrong one, so I'm going to this one, okay? So it will first build for dev, and then deploy a pipeline for dev, because you may have also production projects. So for instance, this is a dev, but you can also have another for production, okay? So in this case, I'll be deploying for dev, so it will do deploy for dev, build for dev, deploy for production. So this will deploy, and then after deployment, you should see this created for you, and then you can create the runs as usual. And then once you are happy, you can authorize deployment for production as well, okay? So which means the steps that you did here for production, you don't do anything. We'll just authorize, and that's it. They will get deployed for production in the similar fashion. So, and that's pretty much about it for that. Now, in this, we mentioned that this created will trigger Azure Pipeline to create the inference, okay? So that's the next stage. So our Azure Pipeline will also have a pipeline for inference. Remember at the graph when we started, I said we have to separate between the inference and so basically the inference and the continuous training. So we are finished with continuous training. So now let's talk about inference. So we have the pipeline for inference. It's in the same similar fashion. The inference will be this code. So let me close this because we are done with these ones. So the inference will just be very simple. So this is the inference, okay? So in the inference, you just create an app which downloads the artifact So it will download the data, the model, it will download the data processor, and then you expose an API. So here I'm exposing 2 APIs, but let's focus on one. So you will expose an API like this one, predict, okay? And then you get new data, and then you transform this new data into this data frame, and then you transform them using the data processor, and then you feed them to the model, and then you return the predictions, because this is the inference phase, and that's it. And then you just create a Docker file to run that code. And in the same fashion, you also create the Azure pipeline, which tell it how to deploy this code. And then this Azure pipeline, once you push this code, this will come here, and then it will match this pipeline, the inference. I can edit it to show. So the inference will the pipeline for inference will connect to this repository, and then it will run the YAML. And then in the YAML, the most important thing is it's going to build the Docker image here. It's going to build the Docker image here. And then after the Docker is deployed, it will create also the drop file. So this is the artifact file. And then into the deployment stage, it will just download those and deploy them to Kubernetes. So I'm telling it to deploy them to this environment, Kubernetes. So the environment, this Kubernetes environment is already defined here. So I've already created 2 Kubernetes environment, one for dev and production. And you can see that it's connected. And I can look that there are services. So this is our pod running inside my Kubernetes, and this is our services running, okay? So this is a separate thing, it's DevOps. So once you run this will run the inference. So I can go, so I will have the inference server run here. So it will look something like this one. It will build and then deploy to dev. If I'm happy, I can authorize it, deploy to production. Now, when I want to test it, I can find out what's the URL for dev, for example. I can go inside the resources, find the URL. I'm looking for the public IP of my Kubernetes. So this is the Kubernetes running, and this is the public IP. Okay, so I can copy this public IP, and then I can try it and pass some value. See, this is some value about houses in Melbourne, and then it will predict. And this is the predictions that it returned. So basically, we are finished with the second stage, which was findings. So I combined both the second, the second was mostly about CICD training. We looked at Azure DevOps, how it does the orchestration. We looked at Kubeflow. We looked at AI platform, how it allows you to create a Kubeflow. And we looked at GitHub as a repository where we're keeping that values. And then Kubernetes is the server where we are hosting our inference, okay? And then I showed you something like this one, which is, this is the graph was created by Kubeflow, okay? And then for continuous training, basically this is what we did. We had the repository, and then we updated the repository, and then Azure DevOps pulled this information from the registries, and then it deployed to AI platform, and then the AI platform initiated a run for training, evaluate, and deployment. Once it was happy, it kicked in the inference by calling the repo. So this is the last stage. And then this repo in return does the inference. And then in the inference, we saw the same thing. The inference starts with this. Azure DevOps pick up the content, the change that you made in your branch. This content could be also the call that came from the training, from the training pipeline. So as we saw, the training pipeline can call directly a branch, in which case it will trigger also an inference to get deployed to whichever server, and then there is monitoring first. So let's go to the monitoring first. So we are going to look quickly at the drift. Yeah, I will share the recording. So let's go to the drift. I'm running out of time, so I'm trying to talk about the drift quickly. So once you deploy your model, the very big issue will become like, how do I know if this model is working properly? Like, sorry, if this model is still working as I expected. So when it gets to production, it will start getting data coming from the customer, the production data. So this data will mostly have slight difference in distribution of the data. So that may impact the model, and you want to be able to trace that and make sure that if that's happening, then you can make something about it. So that's the usual question people will ask, something like, how do I know if the model is still performing? When is the time to retrain the model? So refill the model means when is the time to take new data, train the same model. And sometimes it's even that's not possible to retrain the model. Maybe you need actually to scrap the whole model altogether. Okay. So to do that, what we'll do, we'll have something called data drift and concept drift. So this is our two way of identifying where things are going wrong. Data drift is a procedure where you try to analyze if there are change in the data. So the variables, the feature that you have, are they still holding to the same distribution? Okay, so that's the data drift. Data drift happens when statistical properties of the feature that you used during the training have changed with time. It can happen gradually, it can happen sudden, but usually it will happen gradually. For the case of COVID, for instance, maybe it happened suddenly because people started purchasing things that, they were not purchasing, or because people were staying home, they were having a different behavior. All right, so it can happen anytime. Whereas the concept drift is now when the actual target variable, so let me do this. When the statistical variables for the target change. What does this mean? So this means the decision boundaries or the regression line, it's no longer holding to the truth, okay? Something happened, for instance, as you can see here, the original data was like this, but then a concept drift happened, okay? So, which made the data to the decision boundary to change slightly. So this real concept drift, when it happens, the decision boundary has changed. See, it was this direction, now it's horizontal. There's also a concept of something called virtual drift. The virtual drift happens when there has been a change in Y, but for some mystic reasons, this decision boundary, it's still almost holding, okay? So the same decision boundary that you have, it's still working despite that there has been significant change in the distribution of your Y values of the dependent variables, okay? So let's go quickly. So I'm skipping this one. This is the different way you can get drift. It could be happen sudden, gradual. It can be incremental or recurring, like seasonal, where you see that data will dramatically change with seasons and so on. Now, to monitor drift, you have to use BI, and this is where Tableau comes in. You need a tool that helps you to be able to see this drift happening. So we create a dashboard like this one, but now how do you get this data that you use in the dashboard? Okay, so that's what I'm going to show you quickly. So I have here, as I said, I haven't automated this one, but I'll share with you as well. So this is the audit. I have one file called data drift, calculate drift. So basically this file, because we ran out of time, I'm not going through it, but what it does, you provide it a data set, okay? You provide it a data set here, So you give it a data set, and then it loads the data set. You tell it the baseline. So the concept of data drift, the interesting thing with data drift is you need a baseline and a target. So the baseline is the data set that you consider as your baseline to validate whether the new data is changing. Okay, so this could be the data that you used during the training. You can consider them as the baseline. And now the target is the new data that you keep receiving as people are using your model. Okay, so now because we have the data in one, like we are keeping logging this data there somewhere, so you need to precise the baseline start here and the baseline end here, and the target will be. So basically, imagine you're feeding to this file a big data set, but you just tell the file, split into two, use one as a baseline, the rest as the target, okay? So this will basically do that. We'll create a baseline. It will create a target file, and then it will do analysis of drift using the Kolmogorov analysis, in which Kolmogorov which will basically try to find what's the significance of the difference between the distribution between the baseline and the target for each feature that you have, okay? And not only that, you precise the feature, but also it will be looking at the independent values with the feature. Let's say the feature is postcode, okay? So let's say I want to see for each feature how the distribution changed between baseline and target, grouped by postcode. For each postcode, how different features changed. This is what it does. So it will create that values, and then we save the value in a file, okay? So once we save that, another file that we need is the feedback data, okay? So the feedback data, as the name suggests, it's just after a certain time. So after a certain time, you've run the inference, you've got some people using your API, and then now you have the data, you got also the actual values. So for example, you predicted that this house will be bought for $1 million Australian dollar, and then in the end it was bought 1,200,000. So you have that value as well. So the feedback will be, go back to your data, label, and say, I predicted 1 million, but the actual value was this. So now once you have that value, that's called feedback. So you can run the feedback, you can create the feedback data, and then you use that feedback to do the analysis. So let's go to the analysis. So the feedback data will help you to analyze the concept drift, whereas this file, this one, the KS divergence will help you to analyze data drift. So what's the difference between these two? Between the data drift and the concept drift? The main difference will be with data drift, the data has changed, and then that could have impact, but sometimes the data might change, but there is no impact in prediction. You may still be doing well. But the concept drift happens when the actual prediction has been affected. So in other words, when you analyze the data drift, you are looking to see if the concept drift that you detected could be justified by a data drift. So the analysis of data drift itself can't be used to conclude that the model is doing wrong. It can just infer some information that you can use to make decision whether the drift is significant or not. So in other words, if you've been running this analysis, you may get to the point where, once there is such a big shift in data, it's always going to be a drift in concept as well. So in this case, you can take decision before you can even get feedback, because concept drift is only happening when you have feedback. But now, after a few iterations, you may be able, to learn from the past and say, look, previously I saw this big shift in data. It caused a concept drift, so I'm 100% sure that the concept drift is there, even though I don't have the feedback. So let's go through Tabo. Tableau and look at these two concepts. So we'll start with concept drift. Oh, let's start with data drift, and then we'll see the concept drift as well. So the concept drift, the data drift will be, you basically want to do something like this one, okay? So this data, it's showing me I'm doing the average of p-value. So the data drift created p-value. When the p-value is close to 0, it means there is 100% certainty that this data has drifted. But when it's closer to 1, it means this data has not drifted. And then you also, when you run your Kolmogorov, you also tell it what's the metric it should look like, what's the baseline to call something it's significant drift or not. So for instance, most people use 0.5, 0.05. But depending on the experimentation you do, you can change and increase this value or reduce it depending on what you see. So as for now, we are running 0.0. So every data that returned 0.05, that feature has drifted according to the decisions that we made, okay? So let's go to this Tableau. We'll look at this. It's showing this feature, which is a blue one, the distance. It hasn't changed. There is no drift. 100% sure there is no drift in distance. And this makes sense. Distance doesn't always change. Look, people, when they sell, they'll be selling house within the same region. So the distance for that particular region is not going to change from the center. So you don't expect any drift in the distance unless you start selling a new region unless you move a region. I'm not sure if that's possible. So the next thing we can look, for example, for example, this one, okay, the green, which is the seller, it shows that at some point there was some sort of drifts, but then it went, but this drift was not significant because as you see, we are on 0.0. And remember, we said only when it gets to 0.05, that's when we consider it significant. So it's not significant. So we don't have in this data set anything significant looking at this metric. So you can be sure that, oh, okay, looks like my data is still safe after 6 months. So this is a data for 6 months after the inference was deployed. So after 6 months, really things didn't change too much. You see, in October, something happened, but still. So from June to October, things were still good. Now, to make the situation more interesting, I created a different data set of the same 6 months, but I introduced noise for 2 features. I introduced noise in the rooms, okay, and the property count, okay, the number of properties within the region. I introduced the noise and see what we get. This is the data set with the introduced node. It drifted. You can see it's drifted here. It's saying from September, this is exactly the time when I introduced the noise. This data shifted significantly that it could be affecting your model. It also detected as you can see, it also detected as the rooms were also kind of drifting, but you know, it's still 0.1, so it's still higher than the 0.05. So it's not significant, but it's something you really have to look at, okay? So this is how, and this is just another way of visualizing. So this was by looking at the lines by time, but you can also look at this. So when you start detecting this yellow, it shows, something really happened for this particular feature around this particular month, okay, September. This feature got affected, this greatly affected, and so on. So by just looking at this, you already have red lighting saying, look to your data, your model might be now doing something funny. But at this point, you can't make conclusion because, as I said, the data might change, but it doesn't warranty that the concept has drifted as well. Okay, so this is a data drift, but it's a useful thing you need to look at, okay? Now we look at the data drift. Sorry, the concept drift. So the concept drift which is the most important now. So in the concept drift, what you will do, you will now say, okay, I know that my data drifted, but let me check for the same period if I've observed any significant declining in the performance, okay? So you get that feedback data. So now you've got the feedback. Now you want to analyze the feedback and see if something really happened. So what you see here, let's ignore this side because the way I just did the actual data and I've considered with data that drifted to see. So with the actual data, you can see that it's saying, also it's grouped by, so this is showing the distribution by month. It's saying in June, this is how things were. So for those who have studied normal distribution, you know that the more it's this small and close to the mean, in this case, we are targeting the mean to be 0, then the better, okay? So we can see it's not in 0 because definitely you can't assume that the error that predict the mean error when you're predicting a value in the range of million, you can't really expect to get 0 as your mean. So the mean will be somewhere here, not in 0, okay? So anyway, we can see that it's better. It's not flat, it's tall. And this shows in June, in July, things were good in June. In July, it started to get bigger, but still good. Okay, in August, yeah, still good, like it's still, good. September, like, so as you can see, the more you go further to the month, your data is, the performance is getting affected. So the more it gets flat here, it's just showing there is an increase in errors, in the error residuals. So the residuals are increasing. These residuals are just the difference, the absolute difference between the predicted values and the actual values. So you see when it's increasing, when it's flattening, it just means the value are getting spread towards higher values. And you can observe by the time we reach December, this has already flattened. So it's just telling you for 6 months, this value after 6 months, the prediction after 6 months, it's no longer that good, then you probably need to train, okay? To retrain. So now, this was with the actual value. Now, I also did the same thing with the biased value, the one that I introduced noise, like the drift. So remember, we introduced the drift on September to December, right? So as you can see, June will be good. So now focus on this area. June is good, July is good, August is good. Now I'm going to introduce this one. So see how flat it is compared to this one. See, it's really very flat. This is where this is when we detected the drift, this big drift in September. And then it's being confirmed that the drift actually affected our performance. It flattened. So this is a clear definition of saying, guy, stop and go and retrain. So it even gets worse as we go to the month. By December, it's almost the error is flattened. It's almost everywhere. So I hope this helps you to understand how you monitor drift, concept drift and data drift. And these are just two different ways of visualizing them. I prefer to use this one, but you could also use this one, which just show you how the drift increased with time. And it's comparing between this and this. So this is the unbiased one. This is the one I added bias to show how drift works. And you can see that the drift actually really increased compared to this one, okay? So that's it. I used more time than I expected because I had to explain different concepts, and hopefully this was helpful. After this, we'll go and edit the notebook to make them more readable and add comments. And then by the time I finish everything, I will send an email with all the details of where you can find the code, including how you create this drift and the code used to create this drift analysis. And the one last thing I can add is that when you deploy a machine learning project to production, don't overkill it. Don't try to use everything that you've read. Start with smaller steps like the ones that we just saw. Start with a very simplified monitoring like this one, the one that's looking to residuals versus data drift, and then automate them as you go. And with time, then you may have some other tools like Azure has tool for drift. And so those are tools very expensive that you can adopt when you start seeing profit and you can justify the return on investment. So if there are no questions, I think we can end the presentation. So I don't see any. Let me check if there are questions. Yeah, thank you everyone for, I'm happy that you liked the presentation. I went through them quickly. It was a hard one, but I hope next time we'll do even better. So someone asked, how is the view of the deployed? How is the view of the deployed model? So I don't understand the question properly. Saying thanks, how is the view of the deployed model? So you're asking, how did I get the deployed model? How did I get these values? So I ran on the separate. So I simulated the scenario when someone used the model, and then I corrected that data, and then I used them as a feedback, if that's what you're asking for. Yeah. So, okay. So you're saying, how does the deployed model look like? So the deployed model, the deployed model is the one that I showed you. So if you remember, this is the one, when I hit this is the deployed model. It just gets a bunch of data and it returns predictions. Does that answer your question? So, so looks like there is no more question. Okay, yeah, I've answered it. All right, so in Facile AI, we are preparing a course which will now take people through this step one by one. It will be a course that will probably take 1 week to finish, and you'll be the one informed once it comes. And it might be a premium course, but will definitely give will provide reduction for those who participated in our sessions. We want to be able to make this knowledge available to everyone. So this will be definitely touched upon again. Now with clear examples and one by one, like step one by one, it will be a course which will be deployed hopefully into some of those platforms that sell calls. But as I promised, this content, this whole code will be shared with you. Thanks for participating. Please, before you leave, make sure you type in the country where you were located so that I can know exactly people I was talking to. And I hope to see you anytime soon. Send me the comment if you can. Sorry, the country, I forgot to ask this, but if you can, please, post the country where you're located, and I'll be very glad to know where you were located. I'll see you. Bye-bye.